Hi, my name is Misael Alpizar. I'm going to present the study of silver losses in the lead blast furnace slag. Silver losses in the slag of up to 200 grams per ton are promoted by the current condition of the blast furnace and the settlement tanks. We see that as we lose 200 grams per ton, we see a loss of nearly 120 USD. This financial consideration is the driving force behind studying the process and seeking ways to minimize silver losses. We have to know that there are two mechanisms of silver losses in the settlement tank. Chemical form, that is that silver has a strong affinity for space, copper, antimony, and also can become part of the slag. And physical form, when the bullion has a high silver content, it can become mechanically trapped. This is because mainly for the viscosity of the slag. That is a critical parameter for achieving separation. In the results and discussions, we see that we obtained more than 13,000 slag samples. These were analyzed from 6 furnaces. The result shows a correlation between the analyzed regions of calc-silicate and zinc, copper, and sulfur, and others, and their effects on the silver content in the slag. With these datums, we can do a multivariable regression statistical model that presents a good fit for response as indicated by the Earth square value of 0.7. This is adjusted by R squared. The mathematical model is presented by it is shown in the graph, in the plot. The red line in the plot means all the datums and how it are increased increasingly by the content of silver, and the line in blue represents the mathematical model silver losses that are calculated, and we can see that it is a good mathematical model. This mathematical model only operates only operates with the current operating range that are in the table 1. We show you the compounds, and we also can obtain the optimum operating values that are the best operating values that we obtain from the mathematical model and the statistical analysis data. Also, we obtain a correlation matrix. As we can see, the copper in the positive range is the parameter that most affect the silver losses, and is the most important that we have to take in count. In other hands, we have the oxide calcium that is a negative parameter. So this means that as we increase the compounds of oxide calcium in the slag, we are going to reduce the silver losses in the blast furnace. So we can see in the plots the distributions and density, and we can see how the current operating range are calculated, and also we can see that we show you in the correlation matrix the sign positive and negative, and how the pending is in the scatter plots. This for the last is the result of heat transfer simulation. This shows the temperature profiles of both phases, bullion and slag, and in the settlement tank according to the operation condition. This shows us how the losses of heat are occurring in the blast in the settlement tank, and how the phases are separated. The profiles indicates that we have the slag in the top part of the of the settlement tank, we are going to have less losses of heat, and this is affected by the viscosity. Viscosity is such a parameter because we, as we reduce, as we see that the heat is loosed, we're going to see an increasingly value of the viscosity slag, and this is affecting all the mathematical model and the parameters that are in the distributions and the scatter plots. So we can see that we obtain a multivariable regression model that predicts silver losses in the lead blast furnace. We have an analysis of operational range, highlights frequent furnace operation. We see that copper and sulfur, as assessed by a correlation matrix, significantly contribute to silver losses due to the matte phase formation. We see that oxide calcium conversely has a strong negative effect, reducing silver losses. And we see that temperature profiles indicate heat losses in the settlement tank and increasingly slag viscosity and result in a trapped bullion.